Hello. This is video 68. And almost a summary of just about everything we've done in theory boils down to a fairly, well, I'm going to claim it's a fairly straightforward statement. In the worst case, which is what we're almost always interested in the worst case, comma, bubble sort. Ah, yes, those are the days. Good old simple bubble sort. Life was so easy back then. That says bubble. In the worst case, bubble sort is order n squared. And I hope we have some inkling of what that means now. Whoops. I get out of the picture just a little. Sorry about that. That's bullet point 1. Bullet point 2, merge sort is order n log base 2 of n, which we derived with perhaps a mild amount of pain and suffering in the last video. But there you have it. It looks like bubble sort is preferable, doesn't it? N squared, that's a simpler expression than, good grief, n times log base 2 of n. That just doesn't look very user-friendly at all. But you know what? Let's make a table. Also, for old time's sake, haven't made a table in a while. I'm going to say that this is list size n over here in this column. List size capital N. There, that's simple. What would be a simple list size? 2. Aw, that cute little list, only 2 elements. That's a simple list size. Pardon me, but I need some more columns. Tables need more columns. And I do drink of water. Log base 2 of n. There comes that log again. Let's ramp it up. N times log base 2 of n. Let's ramp it up even further. And the last column over here, n squared. And since this is a table, I mean, they don't necessarily, well, they do a little bit. I was going to say they don't depend on each other, but they kind of do. Let me do the easy one. If the list size is n, then n squared is 4. And I'm interested in that because I want to know how bad bubble sort gets in the worst case as the data set gets larger and larger and larger. Okay? What about log base 2 of, well, I got to remember what log base 2 of n even means, or I can't fill this in. Log base 2 of n. You can sing it along with me. Log base 2 of n is the exponent you have to put on 2 to get the number. Log base 2 of 2. What exponent do I have to put on 2 to get 2? I got to put 1 on there. That was a lot of discussion just so I could write a little 1 down there in that column. But this says if I take 2 to the first, I get this. Now, that makes this one easy. Multiply these 2 columns together. N times log base 2 of n. Here's n, log base 2 of n. 2. I did that math in my head. Ramp it up. Let's go to the next list size that I'm interested in. I'm making these come out even on purpose. I could do them with numbers like 3 and 5 and 9 and so forth, but I'm going to get decimal fractions here that'll be really ugly. It's just going to work out more smoothly because of this logarithm here. If I stick with powers of 2, what exponent do I have to put on 2 to get 4? I got to put a 2 on there. Let me double check. 2 raised to the second power equals 4. Yes, indeed. How do I get the third column? I multiply these 2. N is 4. Log base 2 of n is 2. 8. What about the last column? N squared. 4 and 4 is 16. See if I can pick up the pace just a little bit. The next list size I might be interested in is 8. Log base 2 of 8, the exponent I've got to put on 2 to get 8 is 3. N times log n, 8 times 3 is 24. N squared, 8 times 8 is 64. Just a few more. 16. The exponent I put on 2 to get 16 is 4. 2 is 16. These 2 multiplied together, I'm going to have to cheat and look, is 64. 4 times 16 is 64. 16 squared is 256. Couple more and then we're done. 32. What exponent do I put on 2 to get 32? Put a 5 on there. You can test it and see. 2 times itself 5 times is 32. What about 32 times 5? That's 160. I hope you see how I get in these columns. If not, you might want to back up a little bit and look at the easier rows first. I'm working my way up here. Actually, all of these are calculated based on n over here. I got to know what n is. How's that for a stall? 32 times 32 is 1024. One more, and then it's dot time. 64 dot dot dot. What exponent do I got to put on 2 to get 64? How about 6? What's 6 times 64? Well, if I wrote it down right, it's 384. If that's wrong, I got it wrong on purpose. See if you're paying attention. Oh, I think that's right. Okay, and 64 times 64, 4096. Dots all around. Now then, these tables, these columns in this table, they are trying to tell us something. If we will only listen. Look at what's happening to the list size over here. I double it every time I go up here. The order of magnitude of an algorithm, its whole reason for existence, is to try to tell us how bad things can get as the list size gets bigger and bigger and bigger and bigger. Here's the one we already know about. Bubble sort, we already know about. Double, 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 double. Each time, look what happens. Order n squared is proportional to the square of the size of the data set. In other words, in our case, the square of the length of the list. So look, this corresponds to the number of comparisons we're going to have to do in the worst case. It gets huge in a hurry. Size 64, it's got to do 4096, approximately 4096 comparisons in the worst case to get this in order. Yikes. What about this column? Who is this, by the way? Oh yeah, merge sort is order n log base 2 of n in the worst case. Here's the deal. Think of it this way. N squared is n times n, another n. This is n times something that's smaller than n. This column was n times itself, something big times something big when we get to these larger numbers. This column is something big times something a lot smaller. This is growing very slowly. Log base 2 of n doesn't get big in a hurry. It gets big very slowly. So, what does that mean? That means this, which is proportional to the worst runtime for merge sort. The growth rate of the number of comparisons we got to do with merge sort, that complicated algorithm that splits and splits and splits and merge and merge and merge, it seems like, you know what, that's got to be more complicated than bubble sort. And to understand, yeah, it is more complicated than bubble sort. But for the machine to do it, it takes a lot less comparisons. It was woven into the discussion, you might have missed it, but a lot of it has to do with cutting out comparisons we don't have to do anymore. To find the smallest thing in the whole list, we don't have to look at the whole list anymore. We look at the first number in each one of the two halves. And that finesse away all the extra comparisons, that works its way all through the algorithm. You don't have to remember any of that. You do need to remember this. The merge sort, look at the growth rate of this. By the time n squared is up to 4096 for a bubble sort, n log n is only up to 384. So this algorithm, especially when we get to really large lists, 64 is not such a big list to have to sort. 64 million, that's a pretty big one. Oh, that's going to take a long time with merge sort. That might take till next year with bubble sort. That gets huge relative to our n log n merge sort. That, ladies and gentlemen, is why we care about it. Algorithm analysis, why we want to look at more than one design of a mousetrap. We want to look at more than one sorting algorithm, compare those. These are hypotheticals. This is what we predict will happen as the list size gets larger and larger. And if we were to run it, get empirical evidence, run it, some time trials, find out how many comparisons it actually does. These are ridiculously close to what you actually get. It really does go a lot faster with a more complicated, unfortunately, with a more complicated algorithm than bubble sort. Sometimes simplicity, even though it's great for implementation, it's not so good in practice. That's why computer people that know these things and can use these things in their daily lives as programmers Some of them can make the big bucks. Okay, that's probably a kind of a weird, complicated way to end things, but let's just drift off into theoretical space out there in the galaxy that I drew on the board the first lecture. That's where we are. We're now floating around in space. I'll see you out there and online.